So, hi everyone, welcome and thanks for coming to the seminar of Nenad Kralj, who is currently in the middle of a move to the University of Rijeka. And so just to say a few words about his CV. So he started studying physics here at the University of Zagreb, got his master's, then got a PhD at Camerino in Italy, then moved for postdocs to Yale and to Copenhagen. And most of his research career, actually, he did optomechanics, so mechanical membranes interacting with lasers. And it's experimental, so he worked in mostly in experimental labs. So today we'll talk about optomechanics and the work that has been published this year and last year, and I'm very excited to see what it is about.
Yeah, thanks, Sheila, for the introduction, and thanks everyone for being here and having me. And exactly as you mentioned, I will tell you a little bit about the, let's say, part of the recent advances in optomechanics, in particular, the transition towards room temperature while having the system operating in the quantum regime. And the second part will be about how this system can be exploited to have a sort of a quantum memory for single photons. And then I'll give you a little bit of a taste of something slightly different, some non-Hermitian topological physics. So I don't know if this is necessary or not, but I would prefer to start the talk with a little bit of a background and introduction of optomechanics in general. So basically the main constituent of every optomechanical system in one form or another is some sort of an optical pattern. And when I say optical, it can also mean microwave, but what I will be talking about is mostly near infrared or telecom. And let's say a paragon or the archetypical optical cavity is just a linear fabricating. So you have two very reflective mirrors facing each other. And then you shine laser light from one end, or if you want multiple ports, but typically from one end. And if you hit one resonance of this cavity, basically, you have, owing to the different resonances, you have this sort of profile in transmission, and basically you have the inverse of this in reflection. So in other words, if you hit one resonance of this resonator, then you have a peak in transmission. And this is pretty much the whole story. But if you then assume that one of the end mirrors is free to move, you can imagine it as a mirror on a spring. Then something more happens. So basically, the light feels the motion of this mirror, and the motion can be either generated or induced externally by some force that you wish to measure, or a thermal Langevin stochastic force. Or in principle, it can also be induced by the light itself, because if you think about it a little bit, or you remember your basic physics, then light carries momentum. And this is, I don't know if it was the first observation, but it's commonly cited within optomechanics community that this was first realized by Kepler, noting that the tails of comets always point away from the sun. So this is owing to radiation pressure. It's also the, let's say, phenomenon behind the idea of a solar sail, if you will. So anyway, because of this motion, it basically modulates the phase of the intracavity light. In other words, some of the light from your laser, from your carrier, is scattered into sidebands. And then you have this so-called red sideband, so a lower frequency sideband, which is commonly called Stokes, and a blue sideband, anti-Stokes. And basically, the anti-Stokes process corresponds to, so if you see, if the light is shifted from the carrier to the upper sideband, that means that it is upshifted in frequency. And the difference in energy comes from a phonon in the mechanical mode, which has been absorbed by the photon. And this means that basically this anti-Stokes scattering corresponds to cooling of the mechanical motion. And vice versa, the Stokes process, basically this scattering corresponds to the photon losing a certain amount of energy, namely the energy of a mechanical phonon, and it's deposited in the mechanical mode, so it heats up the mechanics. But the important thing is that if the carrier is on resonance with the optical cavity, then these two processes are in equilibrium. And so basically you get no net cooling nor heating of the mechanical resonator. What you do get is just a more sensitive interferometer, owing to the fact that the light is reflected many times because the mirrors are highly reflected. So effectively you have a higher sensitivity to any displacement of this mirror. I'll come back to that shortly. But basically, maybe now you can already sense where I'm getting with this. If you then detune, which is to say, shift the frequency of the carrier with respect to the frequency of one cavity resonance, then you induce an asymmetry between the Stokes and anti-Stokes processes. And in particular, if you park your carrier to the red side, meaning a lower frequency compared to a cavity resonance, then the cavity enhances the anti-Stokes process and you get an overall cooling of the mechanical mode. And again, vice versa, if you park the carrier to the blue side, then the Stokes process is enhanced and you get heating and instability. Formally, I would say that in the interaction picture, the full optomechanical Hamiltonian, when you do the rotating wave approximation, so basically you do a linearization of this Hamiltonian. I don't even know if I want to talk about these different prefactors here, but basically the Hamiltonian is proportional to these two terms. So the optical resonator or the cavity mode and one normal mode of the membrane, they're here on equal footing. And you can see that there are basically two types of products. So there is this A dagger B and its complex conjugate, and then there is A dagger B dagger and its complex conjugate. And the first two are what is called a beam splitter like Hamiltonian or a swap. So basically you can see that you create an optical excitation by destroying a mechanical one and vice versa. So this one is enhanced when you're on the red side. And instead, you have this sort of two-mode squeezing type Hamiltonian when you're on the blue side. And interestingly enough, in the onset of optomechanics, I guess before it was even a field in its own right, it was actually this process that was of interest in the context of interferometric gravitational wave detectors like LIGO, where the Russian theorist Draginsky noted that this might lead to instabilities because, you know, I suspect, or I know actually, that what they want to do is park their laser on resonance, but since the lock is never perfect, then they might spend some fraction of the time on the blue side. And if the pump power is too large, that might lead to instabilities, because as I will show you, sort of, this heating actually means that the mechanical line gets narrower and narrower. And so the amplitude basically explodes. And so your locks will become unstable and so on and so forth. And I mean, this is still of interest nowadays because this two-mode squeezing obviously can, you know, lead to entanglement between an optical node and a mechanical node. And then if you also imagine like a two-tone pumping, one on the red side and one on the blue side, then you can use the other interaction, the swap interaction, to basically just use a mechanics as a mediator, and then you have robust entanglement between two optical nodes. But somehow most of what I'll be telling you about today is related to having the optical pump on the red side of an optical resonance, and then essentially talking about this effect of cooling the mechanics. And it's typically called sideband cooling because of this sideband picture. Okay, just to give you a little bit of a taste, this schematic is actually somewhat obsolete these days, but still you can see that at least the mechanical resonators comprising these optomechanical systems vary in mass and corresponding to frequency and size. So there are these toroids, which would then be coupled to evanescently from a waveguide. There are these waveguides which are patterned with holes. These days, these are known as optomechanical crystals. So basically, these holes serve simultaneously as a ring optical cavity, but also they have a certain breathing mode, so it's also a mechanical resonator. Yeah, like clouds of atoms, micro and nanoparticles, as I sort of already hinted at, macroscopic end mirrors of large interferometers like LIGO. And what I will be telling you about mostly is related to these type of membrane resonators. Which, well, this image is also obsolete, but I use it deliberately because I will mention sort of how we got from where we were, let's say 10, 15 years ago to where we are now. So basically, this is a thin membrane. It's a silicon nitride membrane. It's a layer of silicon nitride, which is deposited on a silicon wafer. And then within one window of, let's say, 1 millimeter side length, basically the silicon is etched away and you're left with a rectangular silicon nitride membrane, which is, well, these days the thickness can vary between 10 nanometers and let's say 100 nanometers. And basically what is done with these membranes is that they're placed inside a fabricating cavity. So instead of having a movable end mirror, you replace this movable mirror with a membrane, which is now a mechanical resonator. But the principle is pretty much the same. So if you imagine, you hit a resonance, then a standing wave forms. And basically this intensity profile, or the standing wave intensity, it pushes the membrane, or the membrane moves because of thermal force. And since the membrane is just a slab of dielectric, so as it moves with respect to the intensity profile, the light feels its presence more or less. And as a result, the effective path length, or the effective length of the cavity is changed. And in turn, this also means that the resonance frequency is changed. And this then means that as the membrane moves, the standing wave needs to readjust to account for the new resonance condition. This takes finite time, and then all these things like cooling and heating can take place. And just to be mathematically concrete, so you have what I will be telling you about is just I will be talking with one optical mode of the cavity to one normal mode of this membrane, which we can reduce to a 1D resonator. And this resonator has some intrinsic damping rate because of its coupling to its thermal environment, which I denote as gamma m. And also the optical mode of the cavity has some decay rate cut. And so if you want to do cooling, right now that you introduce this red detuned beam, you've coupled your mechanical resonator to this optical bath, which because of its high frequency, even at room temperature, it's essentially at zero occupancy, which is why you can do cooling to begin with. So you're taking excitations from the mechanical mode and pumping it into this bath, which is essentially at zero occupancy. But your mechanical resonator is still also coupled to its intrinsic thermal bath because of it, it's clamped somewhere or something like this. There are still dissipation mechanisms. And then if you want to find the overall occupancy that you will reach, you can find it with this principle of detailed balance. So basically it's coupled to its intrinsic bath, the occupancy of which I denote as N thermal. And then there is this optical coupling due to the presence of this pump. And I told you that this optical bath is essentially at zero occupancy. That's not quite true because there is still quantum back action, which in this case is manifested by the presence of this Stokes sideband. So, okay, sorry, I forgot to mention, but because I told you that the cooling is essentially a consequence of inducing an asymmetry between, the rates of these two processes, and the asymmetry is induced by the cavity. So what you really want is to have the cavity favor only one process. And then you can also see, because the sidebands are separated from the carrier by the mechanical frequency, that the condition for efficient cooling is that the cavity cavity line width is much smaller than the mechanical frequency, because then it basically distinguishes between the sidebands. So this is called sideband resolved regime. If instead I have a very wide cavity, then if I even detune a little bit, the asymmetry is not as pronounced. And as it turns out, I cannot go to the ground state in this case. I will not tell you specifically that this is true, but just take my word for it. But anyway, even if you are in the result sideband, which is to say that this Stokes process or sideband is far away detuned from the cavity, it still exists. I mean, this is a Lorentzian, and its tail goes all the way to whatever, zero. And so there is still a small presence of this Stokes sideband, and this is what gives you this minimum occupancy that you can reach. But anyway, for all intents and purposes, let's say this is pretty much negligible. It's not quite true, but let's just stick to this for now. And then I can reduce this entire expression to something like this, where this CQ is the so-called quantum cooperativity. And I will not bore you with all of the terms, but basically you can see here, well, three things I need to point out. So you want to boost, if I assume that this quantum back action is negligible, then I'm just left with the reciprocal value of CQ. And if I want to go to the ground state, the optomechanics community has sort of determined that what we will use as a benchmark for a ground state is that the total final phonon occupancy is smaller than unity. So that we take as a threshold for being in the ground state. And you can then easily see that this is basically equivalent to saying that CQ has to be larger than 1. And so, of course, in principle, I want to boost it as much as I can. But the prerequisite for quantum operation is unity. That's the threshold. And from this expression, you can see that obviously a high finesse or a low optical line width is favorable. I want to have a high Q, or alternatively a small mechanical intrinsic decay rate. And yeah, I haven't shown you the expression, but the thermal occupancy is essentially proportional to the bath temperature. So cryogenic cooling makes things easier. Yeah, and then basically to sort of flip the thing on its head, you can sort of from this expression see maybe why, well, one of my former supervisors actually had the idea of not using an mirror as a mechanical object, but a membrane. Because then you can sort of separate these two conditions on the optics and the mechanics. You can have a very high reflective mirror to have a small kappa or a high finesse, and not worry about its mechanical properties too much. And then on the other hand, you have just the silicon nitride membrane where you lose the focus on its mechanical Q. Why silicon nitride? Well, that's sort of a twofold answer I could give you. First, from the optical side, because at, well, 1064, and if you want to do some other stuff with telecom, as I'll show you later, the reflectivity of silicon nitride at these wavelengths is sort of, non-zero, but not too high. Why do I not want to make it too high? Because, well, if that approaches unity, then effectively I'm going back to having an N mirror as the mechanical resonator, and in a sense, then I don't really require one of these two mirrors anymore. And so I'm basically going back, which is not what I want. So the reflectivity, depending on the thickness, is something like 20%. The second reason is because it has very low intrinsic losses. And then I can tell you basically, in my mind, there are three stages of the advancement of the mechanical Q factors of such resonators that took place over, I don't know, the course of the last 15 years. They first started with membranes exactly as the ones depicted here. So this was commercially, I guess still is, commercially available by a company called Mercada, with Q factors something like 10 to the 5 at free temperature, very ultra high vacuum. And the nice thing about this and basically why silicon nitride is nice is because they use this principle of dissipation dilution, it's called. So basically, eventually, your losses are limited by the intrinsic losses in the material. And so you cannot do anything about it other than increasing the conservative part of the energy such that the Q factor is sort of effectively enhanced, and you increase the energy that is stored in the mode by applying stress to the material. And so these membranes are very taut. Eventually, this also has a certain limit. And then people had the idea of some sort of phononic shielding. So the first iteration of the phononic shield in this sort of membrane, okay, this one is, the difference between these two is that this one, so the brownish looking thing here is basically the window here, which is the silicon nitride, and it just so happens to be circular. In this case, that doesn't matter. But the grayish thing around it is the silicon wafer. And as you can see, there is some sort of periodic array of holes. And basically what this does is it opens a band gap at a particular region, frequency region, around some nodes of this circular thing that are of interest to you. And this band gap radiatively shields these nodes from the outside and vice versa. And this boosts the volume factor. But the third generation, which is what is sort of the benchmark these days, and it's actually the idea stemmed from the group of one of my previous bosses in Copenhagen, is this so-called soft clamping. And I will tell you about this on the next slide. So basically the difference between the second generation and the third generation is a simple one. Here, the holes, the pattern, the 2D crystal, if you will, of holes is patterned in the silicon, whereas here it's patterned in the silicon nitride. And this is a subtle difference, but it's an important one, because people realize that eventually you become limited by the bending losses at the clamping point with silicon. So I'll just try to illustrate it here. If you imagine that you have something, square, which is not really the case here, then the normal modes go as like a sine function in either direction. So basically the mode would like to oscillate out of plane as this dashed green line here. But because it's clamped to the silicon, basically you impose a boundary condition that the out of plane displacement here at that point has to be 0. So you're bending it, and this induces losses. And the way soft clamping solves this issue. So what is soft clamping? Sorry, I'm going back and forth. Basically, well, you can't really see it, but still the thing that is on the outside, that's still silicon. And in the Mercada case, this window was just not patterned, that's silicon nitride. It's still silicon nitride, but now it's patterned with a periodic array of holes. And then we make a defect in the center, which is to say we make a pad, which is slightly larger or smaller, if you will, in the center. The periodic array of holes creates a band gap, which radiatively shields the center, as in the case of having the holes patterned in silicon. And then the pad basically is engineered in such a way that it supports some normal nodes within the bandgap. And the difference between the previous generation is because the holes are, so here, basically this is a Microsoft image, and the white areas here are silicon nitride and black, that's just a hole. And this small thing here is my pad of interest. This is what supports my, as it turns out, very high Q mode. So over 100 million of full temperature. And the reason why this boosts the Q is because the holes are patterned before the clamping point with silicon. So whatever mode there is, it's allowed to decay freely before it reaches this clamping point. And so basically here and here, it's bent as it was before in a standard hard clamping scenario. But at that point, when it reaches it, I mean, the out of plane displacement is already zero. So there essentially is no bending there because it's already decayed. And that's the boost basically between the second generation and third generation. Anyway, okay, so we have this high Q mechanical mode. We still place it inside an optical cavity, and we can do cooling with the recipe that I told you about in the first slides. And what we want to do is we want to try and have CQ larger than unity and do some quantum stuff, but without the necessity of having cryogenic pre-cooling. So just optical cooling from room temperature. Well, why? Because, you know, it can lead to interesting applications, and one of which I will tell you about in the form of this quantum memory. And for these applications, it would be nicer if you didn't have to have each of these systems, maybe as a node of your future quantum internet, having to be in its own class or something like this. And it turns out that our optical resonators and the mechanical resonators that we have, they're both of high enough quality that we can reach this, prerequisite on CQ even at room temperature. And so, you know, then you might ask them, so what then is the problem? Well, the problem is that as you cool your mechanical resonator of interest sufficiently, eventually the change of the resonance frequency of your optical node is not predominantly determined by the motion of this resonator, but of certain modes of your end mirrors, which are at the same frequency. And these are very low Q, so you can't really efficiently cool them, at least not optically. And basically, since they are, you know, driven stochastically by some thermal force, they bear no phase relation to your mechanical resonator of interest whatsoever. And so you cannot cool them, and they set a limit to how well you can cool. And basically, then you have to engineer the spectrum, the vibrational spectrum of the cavity and mirrors. And we thought of two ways of doing this. And basically, one idea is to reduce the mirror size, with the idea of having it so small that even the basic normal mode of this mirror is higher in frequency than whatever mode of the membrane we are talking to, and that mode is around the megahertz. And one idea of reducing the mirror size is to have a fiber mirror. So basically, you take a fiber, you ablate it with some CO2 pulsed laser, and then you coat that, and there you go. It's a very low mass mirror. And in principle, this could work, but there are still mixing, you know, of different nodes and so on. As so happens, also some hanging nodes. So we wanted to use also a different strategy, which is to create a bandgap, sort of like the second generation of the membranes that I told you about. So basically, we take a thin Pyrex layer, you know, that's our mirror. We coat it with some high reflectivity coating, but on its backside, we bond it with a silicon 2D periodic structure, And this structure then creates a bandgap at the center of the mirror, and it's engineered to have a bandgap in some frequency region that we want. And basically, we open it around the membrane node that we want to talk to. And so here are the two, driven, in this case, spectra. The blue one is on the edge, where basically this thing does nothing because you need a separation of a couple of unit cells to really feel this this band gap. And then the red spectrum is at the center, and you can see that it's a couple of orders of magnitude lower. And by the way, this sharp red peak, please don't mind it. That's just an external calibration tone, so that's not a real excitation of the mirror. And so there you go. The motion is suppressed where you want. And so you have two options with these two types of mirrors. Either you can make a fiber cavity, or you can make a fiber and exoskeleton mirror. We call it exoskeleton because it has this silicate structure on the outside. You can't really do an exoskeleton with an exoskeleton because the bonding only really works if the mirror is flat. And two flat mirrors, they form an optical resonator, which is on the boundary of stability. So in principle, you could do it. That's really not something I would recommend. And so for reasons of, remember, we still want to place a membrane somewhere in the middle. And we have to be careful about how it's, well, in particular, in this case, the angular alignment with respect to the cavity node. So we want to make the membrane perpendicular to the cavity axis. And because these mirrors, these fiber mirrors have a small radius of curvature, then the cavity will have to be very short. It might be difficult to fill the membrane to a sufficient degree. And so we opted for a combination of an exoskeleton and a fiber mirror. And this is basically the schematic of the design. This is a photo. So we have two aluminum blocks, basically, which can be screwed and unscrewed without the loss of alignment, as it so happens. On one side, we have the fiber mirror, which is glued to a shear piezo. That's just for tuning the cavity length and locking it. And then on the other side, we have this sort of sandwich between the exoskeleton and the membrane. They're just clamped together, and there is a spacer between them, and this is actually nothing fancy. It's just kitchen grade aluminum foil, 16 microns thick. And yeah, so what did I want to say? These are some parameters of this cavity. I don't know, pretty modest finesse of a couple of thousand. It's quite short, which is what makes things difficult in its own right. It has to be short, as I said, because the radius of curvature of the fiber mirror is some hundreds of microns. But then basically the fact that the cavity is short, it means that it's going to have a relatively large line width. And so I'm not going to be sideband resolved, which is to say my mechanical frequency is going to be way smaller than the optical line width. And I told you, if you remember, then that means that I cannot go to the ground state by just using sideband cooling. There is still a trick, which is to do feedback assisted cooling, which is not something I told you about. So basically, we measure the displacement of the membrane with a resonant beam, and then we filter it with a tailored controller, and we basically adjust its width and the gain of the feedback, but also the phase at the mechanical frequency. Basically, we adjust the phase such that the force that we will exert from this measurement is a friction force. And the way we exert the force is, this is a small schematic. So basically, we have two beams actually impinging on the cavity. One is resonant, and that's basically for reading out the motion. And then the blue one is detuned. This is going to be my optomechanical cooling beam. And it's detuned from the red one via an acousto-optic modulator, which also has an amplitude modulation port. So we basically feed the measurement of displacement to this amplitude modulation port, and then that creates sidebands. And basically this beat note between the cooling beam carrier and sideband is going to be what's going to create my additional feedback force on the membrane. being that this is a sort of measurement, feedback technique, then there is an additional, there is always a certain imprecision related to our measurement of displacement. And basically, for a high enough gain, this can start to drive my mechanics. And again, set the limit to how low I can cool. And so in other words, I want this imprecision to be as low as possible, or put another way, I want to have a very, not only a strong measurement, which is to say I want to have a high CQ as before, but now I have an additional constraint, which is that I want to have a very efficient measurement. So I want to have a high detection efficiency. And basically you plug in these two numbers, and then you have a measure of how low you can ever hope to cool, even for an ideal feedback filter. And so, okay, here it is. This is my mechanical spectrum around a particular, bandgap mode, high Q mode, in displacement units. And basically what I'm showing you here is from lighter shades of blue towards darker shades of blue. I'm just increasing the feedback gain. The gray is shock noise, and basically this is some spurious mode. The mode of interest is the thing to the right. I'm measuring not the real displacement, but the apparent displacement, which also contributes to which also the imprecision contributes. But then I know how to basically play around with this, and then standard optomechanical theory tells me how I can convert this to the actual displacement, and then I take an integral of this, and this is basically proportional to the occupancy in my mechanical load. And here I'm plotting this occupancy as a function of, again, of gain, where the circles are basically, color coded to the spectra on the left, and squares are just additional spectra that I'm not showing here because it would just be too crowded. And one thing you can see is that, so basically the black, solid black line is what I would expect as a function of gain if I were quantum noise limiting. And the dashed line is if I have some excess classical noise. As you can see, clearly, that's clearly the case, which is, unfortunate. It's not what I wanted. We have a couple of ideas of where this might come from. There is something called thermal intermodulation noise. If you have a strong mechanical coupling, basically your mechanical modes can mix. And this is particularly challenging. It's one of the most challenging things when you move to room temperature, because it's more pronounced at a higher temperature. However, we don't think it's that, for reasons I will not bother you with. We've done obviously some simulations. What we think is just bleed through of the cooling beam, and that's even beside the fact that we're offsetting frequency and they have orthogonal polarizations, the readout beam and the cooling beam. But still, the bleed through we think is sufficient to add this excess occupancy. And so instead of going to, I don't know, 20 or 10-ish phonons, we level off at something like 30 or 20. We've taken these measurements at different powers of the readout beam, which is to say different quantum cooperativities. This one that I'm showing you here is at 0.1, but we know experimentally that we can even go beyond, which is to say we will not hit some bistability of the cavity before we go to unity cooperativity. This is interesting because, as I said, unity cooperativity is a prerequisite for quantum coherent swapping of the excitations. And so, yeah, here I think I have a feeling I have to speed up. So here are some, different systems which are close or at the ground state at room temperature. Again, of wildly different masses and sizes. So these are two from the Askelmeyer group in Vienna. These are two different cooling mechanisms of optically levitated nanoparticle, and they're both in the ground state. But their masses are just orders of magnitude lower with respect to the effective masses of our mechanical modes. So naturally, it's easier to cool it. Then there is LIGO, which is in the opposite extreme, and they're sort of still better, but this is a huge, very long interferometer, so they can measure their displacement very accurately. And in fact, this result was actually obtained by also squeezing the light that they probe the interferometer with. So it, it's more complicated in that sense. And this is slightly older, well, with respect to ours, result from the Simon Verbocker group in Delft. And this is sort of this fishbone-like structure, this optomechanical crystal that I mentioned to you. And the reason I'm basically prompting this one is because the effective mass is slightly smaller, but comparable to ours. So it's certainly the closest one out of these systems to our own. And we reach a similar occupancy, and actually both are operated. Sorry, I forgot to mention that telecom wavelengths. The reason I like ours in a way better, well, not only because I've worked on it, but also because our CQ is 2 or even 3 if you want to push it orders of magnitude higher than theirs. So there is in the per mil region, and I don't think they can easily push it higher because the resonator is small and they're limited by basically photothermal effects. If they push the power up, they start heating up classically. But so anyway, this is where we are. We're still not at the ground state, but we have ideas of how to push it. We were basically limited by the detection efficiency, and actually because our mode matching to the cavity mode wasn't very good. In fact, it was very poor because the alignment stage on the fiber is not very precise. So it's a quite, I would hope, straightforward technical advancement that is needed to push the thing lower. Okay. Hopefully, I still have time. I want to tell the setup. Great. I want to tell you about this other thing, which is the optomechanical quantum memory for single photons. So up till now, what I've been telling you about is the effect of the optomechanical interaction on the mechanical resonator. But there is also the corresponding effect on the optical resonator, which is to say the optical mode. And basically, you can see it like this. Because there is a mechanically compliant element, as I told you before, if you pump your node with a carrier, it will acquire motion sidebands, which here I've depicted as this Lorentzians. And then if you come with another beam, it can just be another laser beam, or it can be generated as a sideband of this same carrier, but not mechanically, maybe with a Pockle cell, with an EON. And for all intents and purposes, let's assume that you're so far in the result sideband that basically the lower sidebands are immaterial. You only care about the upper sidebands, okay? Then let's say that I generate this additional beam as a sideband as well of the carrier. Because there is a mechanically compliant element, eventually this sideband, this externally generated sideband, will interfere with the mechanical sideband. It will interfere destructively. And as a result, when I sweep this external sideband across the cavity resonance, it will not experience just the Lorentzian, but it will experience this dashed orange line, which has a certain opacity window because of its destructive interference with the mechanical sideband of the carrier. The name, the effect still carries is optomechanically induced transparency. Clearly, in this case, it's actually an opacity window, but the name was coined in a different optomechanical system where the situation is inverted. So basically, on transmission, the standard transmission of that system is only 0, and then because of the OMIT, there is a transparency peak. And this is what I'm showing you here is the same effect, but in a membrane in the middle where the transmission and reflection are basically flipped. So it's actually an opacity window. And this is completely analogous to electromagnetically induced transparency. So in sort of to come closer to that jargon, you can still have this sort of lambda system. So here you have to excuse me. I think I've denoted N. So I've used N to mean the optical excitation, unlike before, and N is mechanical, just for this image. So basically, okay, you pump your cavity mode, and then if this carrier is turned off, then basically this transition isn't there. The only way the photon can decay is, you know, for it to decay out of the cavity after a certain decay time. But if you turn it on, then there is another decay channel. So you can just go from this mode via a swap interaction. You know, I destroy a photon, I create a phonon in the mechanical mode. That's this transition. And if I leave it on, the process is cyclic. Eventually, I go back, and then I decay outside of the cavity. So that's the more involved decay channel. The usual one just being going from here downwards. These two decay channels interfere destructively, and that's why I get this opacity window. And so here I'm showing you the actual measurement, albeit with a way older membrane, which has a different frequency, but basically you can see the amplitude for, you know, higher and higher powers of this pump as I go towards redder colors. But what I really want to draw your attention to is that there is a corresponding effect in the phase. So there is this sharp feature. And then if you think back again, that, you know, this sharp feature in the phase is related to the real part of the refractive index, and that in turn is related to the group velocity of the light. And so if I have a very sharp feature, then this derivative basically explodes, and I can stop the impinging light. That's the idea. I use this to stop something coming from the outside. I turn the pump off when it's there, and then basically I have something stored in the mechanical mode. I use the fact that it has a very high Q, and because it also has a very low frequency compared to the optical mode, it has a very high, very long coherence time. And then before it decoheres, I turn the pump back on, I restore a photon, and there you go. Hopefully you retrieve your initial state. I hope I have a few more minutes. What would you want from an ideal quantum memory? You would want high efficiency, you would want a long coherence time. If you want to do a Bell state measurement, you have two photons that you want to confirm, that they're entangled, but they don't come at the same time. So you want to store one for as long as you can. That's why you want the long coherence time. Ideally, I guess, because of the existing infrastructure, you would have this memory operating at the telecom sideband. And also, you would like to have on-demand readout. The EIT memories and also using different paradigms like the Duan-Lukin Sirac-Zola protocol, they've all been implemented in Shantit, should I be standing there?
No.
So they've all been implemented in different sort of atomic systems, like vapors, single atoms and ions, and even some solid state earth ions. But I don't know if I want to call it the downside, but maybe the merit of an optomechanical memory compared to an atomic one is that an optomechanical memory is not tied to any intrinsic transition frequencies that exist in a given species that you use. And actually, there are two types of optomechanical memories. One is, well, this one using OMIT, so a red detuned pump. And then there is a different one which utilizes the other interaction that I mentioned to you, the two-mode squeezing. This is used by the Grubbacher group, actually with a lot of success. They've even done some, I guess, preliminary quantum transportation measurements, if you will. Basically, what they do is they come with a blue pulse, and then they generate pairs of photons and phonons. They take the photon and detect it, and the phonon they store. And then they come up at a later point with a red pulse, convert the phonon into another photon and detect that one, and then do basically coherence measurements, correlation measurements, G2. And you know, this is good, but the, let's say, potential problem is that the excitations are generated internally, and it's also probabilistic. So basically, they're limited to having very weak pulses, because if they increase the power of the pulse, then they increase the probability of creating multi-phonon states in mechanics, and that's not what we want. Whereas with the OMIT, you sort of alleviate this. Yeah, you still want to have a CQ larger than 1 for two reasons. First, you want to be able to initiate your mechanics in the ground state before the single photon comes, because otherwise you wouldn't know when you retrieve a photon from the phonon, whether it came from the phonon that was created by the photon that you sent, or by a completely different, unrelated thermal phonon. And the second thing is that you want to be able to read out faster than the mechanically coheres. And basically, this is what CQ is, even if I forgot to explicitly say it. So basically, it means that you are able to talk to your mechanics via the optics faster than the mechanically coheres. And we've done some preliminary measurements of another, membrane in the middle setup using a soft clamped membrane with a high Q with short pulses. So no single photon. It's not a quantum memory yet. It's just to test the efficiency and the storage time that we could expect. And it was done at room temperature. So I'm afraid, unfortunately, I guess I don't have time. But basically, this is the sequence. Yeah, we generate this excitation via an EOM on one of our beams. That creates a sideband. That's basically playing the role of our single photon to be. And then here we do a set of measurements, basically changing the delay, or if you will, the storage time, and measuring the basically the leftover mechanical amplitude. First, in the absence of any cooling beam, so no storage experiment whatsoever, just to see the lifetime of the node. And we actually see that it's lower, so it's something like 23 milliseconds. That's lower than what we would expect based on a prior measurement of the Q. And the reason is that even when you don't have a detuned beam, when you have a resonant beam to use for the readout, as I said before, in the context of LIGO, your lock is never perfect. You might have a slight red shift, and this will cool your mechanics, and correspondingly reduce the lifetime. And okay, so we do a couple of more tests to see the effect of bandwidth matching between our signal, which is a rising exponential shown here, and the line width of the mechanics, which is to say our memory, and also the two-photon detuning in this image here. We do this by sweeping the signal frequency. The mechanics is at a fixed frequency. And basically, the bottom line is that in both cases, we basically reproduce this overall efficiency of something like 40%, and we know exactly why it's limited to 40%. That's because it's actually limited by the coupling efficiency to and from the cavity. So basically, there are additional losses in the cavity that we didn't want, because it's the overlap between the optical mode and the mechanical mode is imperfect, so there's some scattering losses. And basically, yeah, just one very small remark. The idea between this project was, and it's also the nice thing about the OMIT memory compared to this other type of optomechanical interaction is that you can use it with externally generated single photons. For example, from a quantum dot, and then you can have a very nice deterministic source of single photons that you can couple into your OMIT memory. And then you don't have to worry about these problems that the DLCZ protocol has. The problem at the current state of the art is that the quantum dots, they typically generate single photons which are much wider than the OMIT windows that we can generate in our system. And so the idea is to have this, they generate something at 930, and then it undergoes difference frequency generation, nonlinear crystal via a pump at 2.3 microns. The idea is to make the photon narrower by placing this crystal inside an optical cavity of its own to have some sort of OPO and the like. And I'm also exploring some other things. So I'm afraid I won't be able to tell you the last thing, which is some non-Hermitian physics, which can also be done with an optomechanical setup. If you're interested, then find me. Well, just now, I guess. So I'll be sticking around for a few more hours. So I'll be glad to take any questions that you might have. Anyway, thanks. That's it.
Okay, if anyone has questions. So I can ask you maybe about this.
Sure.
Yeah.
You want me to explain? We're using questions to fill the gaps of the. I'd be happy to do that, but if somebody has a question related to what I already talked about, then maybe we can take that first.
I have a question about the quantum memory.
Yeah.
Stuff. So typically in vapors, you store the polarization state.
Yeah.
Here, is this also polarization sensitive? Or, I mean, do you?
It is polarization sensitive. There was a lot of debate about what sort of, if you want to do a storage of an arbitrary qubit state, how would you do it? And one thing is that obviously you have to, you want to store the time mode, or if you will, the frequency mode. So you want to have the photon line width smaller than the width of the OMIT window. Otherwise, it won't be efficient. But I think what I would opt for is indeed the storage of a polarization qubit. And indeed, it does conserve the polarization because basically the conversion between a photon and a phonon works because the sideband beats with the carrier. And this only happens if the two have the same polarization. And so basically, if you wanted to do a storage of an arbitrary qubit, you would probably do a dual railing. And you would split, you would come with an arbitrary polarization, put a PBS, and then one of the OMIT memory in one arm and another one in the other arm, and then without knowing the which path, you recombine, and hopefully you restore your state. So I'm not saying it's it's going to be tricky one way or another.
And what way again would you say these memories are superior to the atomic vapor ones or the solid state?
I don't want to, I don't know what
the numbers are better, right? Like,
well, of some, yeah, not of all. I mean, I think there are EIT memories that have comparable numbers. Ultimately, I would say, one problem is that, as far as I understand, in most cases, at least with these earth ions, the dominant transitions are not in the C-band. So you either have to do some frequency conversion or you have to do cascaded transitions. At the very least, this reduces the efficiency a little bit, or maybe it just makes the overall system more complex. Yeah, but I mean, in principle, this is also wavelength agnostic, you know. I can do more fancy things. I could do like a transducer. I could come up with a photon at one wavelength, store it in the mechanics, then read it out at a different optical node with a completely different wavelength of the light. The polarization will still be conserved if I, if I match the polarizations of the two cooling beams. And then there you go, there is a transducer and so on.
And how reproducible are your mechanical membranes in terms of
They're
frequency?
very reproducible. I'm not the one doing the fabrication, but they're reproducible, and depending on really what you want, you know. I really haven't talked about this, but we have, or they have, since I moved on since then from the group, but they have different patterns of this defect pad, optimized for different things. You know, if it's slightly larger, then you increase the mass. That basically, I don't have it here, but the higher the mass, basically the lower your optomechanical coupling. But on the other hand, what you gain is you reduce the chance of clipping losses, or you can have a larger spot size and so on. And in fact, yeah, sorry, this goes beyond what you asked.
This omega m, you say 1.3 megahertz.
Yeah, different designs, you know, depending on the size of the pad, they support nodes which are, I don't know, you can also scale everything up. The Q changes a little bit, but basically it's still a very high Q membrane. I would say it can range between 1 and maybe 2 megahertz. And in fact, I don't know if I think I put it there, but I haven't referred to it explicitly. So you see here, it's even a higher mechanical frequency. It's because in this case, we used a higher bandgap. So not the first bandgap, but the second one, where the Q again is lower than in the first one. But the reason why we wanted to do this is because there is this hierarchy of different decay rates and resonance frequencies. I haven't really explained it, but basically, yeah, because of if you want the high efficiency, actually the efficiency of storage is highest if the OMIT window exactly matches the width of the photon. Here I put that it should be way smaller. It really shouldn't, but it should match. And then if you don't want to be in something that is called a strong coupling regime, where you can already have like Rabi splitting, and I don't think you want this, at least not for now, in the early stages, then have it in mind that should be higher than this. And still, for similar reasons, you don't want to have the other motionless sideband messing up with your stuff. So you want to be in the result sideband regime. So the mechanical frequency should be higher. And that's why we resorted to a higher bandgap, which is also a trick you can do to go to higher frequencies if you want. But one way or another, you know, depending on how thick or thin you want your membranes and what you prioritize, whether the Q or the quantum cooperativity or whatever, the yield in a given wafer can vary a bit, but it's still quite reproducible. I would say that with the standard designs, the yield is something like 75% for a given wafer. So there is a silicon wafer, and you pattern something like 20 membranes, and 75% of them with the anticipated Q.
More questions?
Can you just practically that if you go back to this Delian, your beam has to be focused in this center of this other Delian, so the might be quite small.
Indeed, yeah. So and you're absolutely right. It's also something I haven't explicitly said. Maybe to start from the beginning. So this is your this G naught is your optomechanical coupling. See here, it also appears with this end cap. So that's the number of intracavity photons. And basically that happens when you linearize stuff. So then you have an effective coupling. Anyway, but the coupling per photon, it depends on some parameters here. It depends on where your membrane is along the cavity axis. So basically you want to be where the derivative is largest between the antinode and the node of the intensity. You want to have, in principle, a small mass and a low frequency, I guess. And this theta is basically the overlap integral between the optical node and the mechanical node. And one consequence of this, or if you will, at the very least, what this can be reduced to is that you don't want to have clipping of your beam. So indeed, your cavity has to have a waist, which is smaller, or at least, you know, the spot size at the membrane position should be smaller than the defect by conservatively a factor of 2 if you don't want to have considerable clipping losses. And one of the reasons why we were able to use this dandelion, so I haven't shown you the other patterns, but they do indeed all sort of resemble different flowers. And yeah, this one I guess sort of resembles a dandelion. Why we were able to use this small defect design without compromising anything, for example, the G0 because of the overlap, is because that's like the nice thing about what is also complicated, namely the fact that the radius of curvature of the fiber mirror is small, so we have to have a short cavity, but as a consequence, also the waist of the cavity is very small. I can't tell you what it is, but I think it's something like 5 microns, maybe. Yeah, and so we can still use the dandelion without clipping. The dandelion is something like, depending on the actual design, 20 to 30 microns across. Yeah, but you're right. I'm not allowed to have a beam which is larger than that, or at least not if I want to do some things efficiently.
Thank you.
Yeah, sure.
Sorry,
Yeah.
what kind of fiber is this actually? I mean, for
This is a
general, what's used in this field? I'm not so familiar. I mean,
this is a typical single node fiber, and yeah.
silica, or what?
Say again?
Or what? Silica, what? I mean,
To be honest, I don't know. I think so,
okay.
but this was fabricated by a PhD student way before I got there. And the only thing that I know is that they had to sort of strip the jacket when before they do the coating. Sorry, not coating, but the ablation with the CO2 laser. And as a consequence, it's super fragile. And one problem that we had is, you know, we just glued it on this shear piezo. And then we would bring it closer and closer until we found some modes of the cavity. But what we didn't know at the time, so unfortunately I don't have a measurement, but we did measure the sort of bare cavity spectrum. So the motion spectrum just of the mirrors with no membrane. And we were hoping to see the band gap, namely this one, and it was obscured. And we think it was obscured by the motion of the other mirror, namely the fiber mirror. But it's not the vibrational mode. It's sort of like, I don't know if you want to call it, I guess it's still a vibrational mode, but it's due to the overhang of the fiber with respect to the piezo. And so, yeah, okay, sorry, I'm not really answering your question. But what I want to say is that it's tricky, and if I had to do it again, I'm not sure I would opt for this system. Since then, people have come up with a better idea, which is to use, you know, some sort of saw, which I'm not super familiar with, to basically etch this type of crystal in a bulk mirror. And then the advantage is that it can be curved, whereas this one cannot because the bonding doesn't work. And then basically you get rid of the necessity of having a fiber mirror. You have your curved mirror, and you can just make your cavity with both mirrors sort of exhibiting this band gap. But yeah, I mean, the fiber is just a standard one, 1550, I guess silica, single mode fiber. Ideally, it would be PM, it caused us problems because then we have some PM and SM components, and then you have a polarization drift, and it turns into an intensity modulation, which is not what we want. But I guess for some reason, I don't know, the coding doesn't work for the PM. I'm sorry, but I'm not 100% sure.
Thanks.
Sure.
Okay, there's no more questions. I'd like to thank our speaker again and
Thank you.